Okay, welcome everybody to the University Lowbrow Astronomers. I believe this would be the March meeting. Also consider that after this, we're going to upload a recording to YouTube. So of course, we got to be careful what we say and do, you know. Anyway, as usual, yeah, except for Doug. As usual, we're going to have our guest speaker first, and then after questions, we'll go ahead and do a business meeting, what stuff we need to cover that way. But first, we're going to have our speaker here because that's what most of us came here for. And I hope I get this right. Dr. Mojtaba, Akhavan-Tafti.
Yes.
I got it pretty close anyway. Is here tonight, and he is a researcher at the University of Michigan College of Engineering. His PhD dissertation was focused on a process called magnetic reconnection, which is an explosive mechanism responsible for generating accelerating charged particles in the solar atmosphere, as well as in our planetary environment, resulting in auroras. We all like auroras. He further completed his postdoctoral fellowship at École Polytechnique, France, in climate and space sciences and engineering at the University of Michigan, where he investigated extreme space weather phenomena in the coronal heating problem, respectively. Presently, Mojtaba is a team member of NASA's Parker Solar Probe, Geospace Dynamics Observatory, and the Sun Radio Interferometer Space Experiment called SUNRISE. He also leads efforts in utilizing solar sail propulsion for studying space weather at a unique vantage point with a new mission concept titled Space Weather Investigation Frontier. Tonight, we're honored to have him here with us to talk about the Parker Solar Telescope and what it has revealed. And I'd also like to do a shout out for Parker Sevchik, who brought us Parker tonight. And we still want to know how that name got applied to the solar probe. So with that, let's welcome.
I just realized that the date is quite off, but forgive that.
Oh, 1 second, if I
Yes.
could, I need a vice president to take minutes before I forget.
I did it at the last meeting.
So Adrian's free this time. Dave?
I suppose.
All right, thank you, appreciate you. Okay, all right, take it away.
Perfect. So I will start. So here's the background. So for those of you who know what Parker Solar Probe is, I will have videos to show you, but this presentation is practically, it starts about how did Parker Solar Probe come about in terms of what were the science questions that really led to the mission even starting as a concept. And then all of the engineering that went into deciding what the mission should look like before going actually into the science. I hope that you get something new out of it. So practically, this is the idea which I deal with a lot in my job these days is how do you start with a very simple science question and build a $1.2 billion mission around it and get the taxpayers to support it. Yeah. How about now?
Charlie, we can't hear the speaker.
Working on it.
This is on.
Well, it's soft. I could hear him, but it's soft.
Can you hear me now?
Oh, a little bit louder.
Zoom must not be.
How about now?
That's good.
Excellent. That's fine. I can point with it too.
Oh, there you go.
Yeah. Okay, you can still hear me, okay?
Yes.
Perfect, thank you very much. So yeah, so I'll start with a video and then I'll go into the details.
Gary Ford, we're gonna play with the.
People around the world look up and see our sun every day. But through a space telescope, it looks nothing like it does from down on the ground. The surface dances with arches of solar material that reach up into the solar atmosphere, an environment of charged particles and magnetic fields unlike anything we experience on Earth. In 2018, the Parker Solar Probe will launch from a Delta IV Heavy rocket and travel approximately 3 months to take its first swing by the sun right through that atmosphere. Over 7 years, it will get ever closer until ultimately it's within 3.9 million miles or 6.2 million kilometers of the sun's surface. That's so close that the previous record holder, the Helios B spacecraft, was 7 times farther away. An important objective of the Parker Solar Probe is to learn more about the solar wind, an exotic stew of magnetic forces, plasma, and particles. It interacts with planetary magnetospheres and atmospheres, which over the eons may have contributed to a planet's habitability. It blankets our spacecraft and astronauts traveling to the moon and Mars. It affects space weather at and around Earth and causes beautiful aurorae. The solar wind also travels at immense speeds, and scientists want to learn why. It leaves the sun at a speed of up to 500 miles or 800 kilometers per second and engulfs all major planets in the solar system. What is the source of the wind? From a distance, it's difficult to tell. Dr. Adam Szabo, the Parker mission scientist at NASA's Goddard Space Flight Center, says, "We've been examining the solar wind for over 50 years, but the wind is processed by the time it reaches Earth. By studying it much closer to the sun, the Parker probe will be able to tell us such things as what part of the sun is providing the energy source for the wind's particles, and how they can accelerate to such incredibly high speeds. It's like trying to understand how a car runs without looking at the motor. It's important to get under the hood to determine the mechanisms driving the actual system." The Parker Solar Probe is the only NASA mission named after a living person. Dr. Eugene Parker, an astrophysicist, is credited with developing the theory behind the solar wind in the late 1950s. When asked why he thinks so many people are drawn to this particular mission, Dr. Parker said, "I assume it's the same reason that I got excited about it. This is a journey into Never Never Land, you might say, where it's too hot for any sensible spacecraft to function. But some very clever engineering and construction has succeeded in making what looks like a very workable mission." Clever indeed. At its fastest speed, the Parker Solar Probe will orbit the sun at 430,000 miles per hour or 716,000 kilometers per hour. That's fast enough to get from New York City to Tokyo in under a minute. It will absorb temperatures as high as 2,500 degrees Fahrenheit or 1,400 degrees Celsius. And soon, it will begin to transmit the data to help us better comprehend one of the least understood phenomena in our solar system, the solar wind.
Sweep investigation consists of 3 separate instruments and a central electronics box. Most of the instruments within Sweep sit on either side of the spacecraft, stare out over the entire sky, and make maps of all the different particles and what energies they're moving at, and what types of particles they are. The purpose of Sweep is to measure the bulk of the solar wind and the solar atmosphere. One of the biggest questions we want to resolve with Solar Probe is how the corona and the solar wind are heated. In order to do that, we need to see if there are waves that are coming from the sun and depositing energy within the solar atmosphere and in the solar wind. So we have a series of sensors across the spacecraft that will collect individual particles, electrons, fully ionized hydrogen and helium, which we call protons and alphas, and other minor ions, and make maps of the number of particles as a function of their speed and energy and type. We take those maps on the ground and we can interpret them to figure out the temperature, the density, the pressure of the solar wind and the solar atmosphere. On the RAM side of the spacecraft, so that's in the shadow of the heat shield, in the direction that Solar Probe is moving around the sun, we have Span A. Span A looks ahead of the spacecraft. It has an electron and an ion instrument, and they can see the entire sky on that side of the spacecraft. On the other side, the anti-RAM side of the spacecraft, we have Span B, which basically looks behind our direction of motion. Span A and Span B are each able to take an inventory of electrons coming from any direction in the sky. And their fields of view, stitched together like the seams on a baseball, the spans combine to give us a field of view that covers nearly the entire sky. But we have one large gap in our field of view, and it's produced by the heat shield at the front of the spacecraft. So we have the Solar Probe Cup as the final instrument within Sweep. The solar probe cup sits on a strut. It looks around the heat shield and faces directly into the sun. When our solar wind or solar atmosphere comes blowing into the cup, if those particles, which are charged, don't have enough energy, they get reflected out by that electric field we've set up. The particles with enough energy to make it past the electric field come in and strike a plate, and we record the current. All we have to do in an individual measurement is sweep in voltage and measure the number of particles that can make it in as a function of voltage. That sweep, when we interpret it, lets us figure out the average speed, direction, energy, temperature, density of individual populations of particles.
The Whisper instrument is made of 2 telescopes that are designed to sit between the 2 antennae from the field experiment and image the solar wind and the corona as we're flying into it. So Whisper is the lightest instrument we've built before. It had really 2 requirements. We wanted to be able to see far from the spacecraft and then be able to track the structures that are flowing out from the sun, and then as they pass the spacecraft, we would see them locally at the spacecraft. The Whisper instrument is the only imaging instrument on the Parker Solar Probe, and it is looking in the direction that the spacecraft is traveling. And what it sees is light scattered by the dust that's in orbit about the sun. But then, once we remove that, what we see is the light scattered by the electrons in the corona, in the solar wind. These measurements that we're making from the Whisper instrument have been made before by other instruments from 1AU, from the distance of the Earth, about 100 million miles from the sun. By getting closer, we're increasing then the ability to see what's really close to the sun. The fact that you're close means that you don't have all this material that's in between you and the object that you're really interested in. And that contributes to background noise. And so you're looking at something that's much more pristine. You're looking at just that object all by itself. By going eventually 95% of the way to the sun, we are going to be able to see what is a dust-free region around the sun. That's going to be exciting. Parker Solar Probe cannot have any imager that looks at the sun directly. So the Whisper instrument looks off of the heat shield that protects us from this very intense heat. And so we sort of peek over the edge of it. We use it as a shield to block out the sun itself. And that allows us to see this very faint glow coming from the corona that's only observed during an eclipse, for example. We're creating an artificial eclipse. Well, eclipses are great, but from the data point of view, I like my instruments better. They're working continuously, round the clock, 7 days a week, 24 hours a day, 365 days a year, sometimes for years.
Fields is in a special place on the spacecraft. The electronics package is inside the spacecraft where most of the electronics are, but all of our sensors are mounted on the outside of the spacecraft. We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield, and then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight, and they get very hot. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field, and together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what fields will do. Solar wind is the escaping atmosphere of the sun. It's the escaping corona of the sun. The corona is heated in a way that we don't understand yet, presumably involving magnetic fields by energy that comes from below in the photosphere. And it's heated to such a high temperature that it can escape the gravitational potential of the sun and become an escaping wind, a stellar wind, a solar wind. Well, the design of the Fields instrument is a new thing for solar wind physics. It kind of combines 2 previous styles of experimentation. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. Then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team, will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly 3D visual models of the coronal magnetic field. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona is just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
ESIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ESIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy, and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle by looking at all the different energy depositions. In our lower energy instrument, we also have the same sort of solid-state detectors, but in addition to that, we use an extra trick, which is when a particle passes through a very thin foil, it ejects an electron. We're able to detect that, and that gives us the start timing for the particles. One of the big issues for ESIS is to understand the difference between solar energetic particles that just come from the sun with a certain energy and those that are energized in interplanetary space as they move outward. By the time they get out to the Earth's orbit, that's all so messed up, mangled up, that it's kind of hard to tell the difference between those. But as we get in closer and closer to the sun, we'll be able to differentiate those two types of sources, which will be really important for understanding the fundamentals of energetic particles in the solar system. By going in close and measuring the detailed distributions of these energetic particles, their energies, directions, and their species, we're going to learn things that we couldn't possibly learn by looking forever from a remote distance. And by understanding our sun in detail, we can understand lots of other stars in much greater detail.
Okay, so I have a few questions for the audience now. So if you were to summarize the entire video in 2-3 takeaway messages, what would it be? What do you think as the audience you were trying to be sold on this video? Any of you paid attention enough? Yes.
You mean about like defense answer?
Yeah. What is really the number one objective of a billion-dollar mission?
And what creates the heat?
That's exactly right. And therefore, to understand that, what do you need that no other mission has done?
Data from inside. Oh, close.
Exactly. Close is key. That's if you were to do the exact same mission close to Earth, it would be only in hundreds of millions of dollars. Whereas when you go so close to the sun, that's where all of a sudden they're extra zeros. And that's really key here too, is that if you listen to every single instrument PI or principal investigator, every one of them talked about how close they're going to be to the sun and how extraordinary and revolutionary that is. And that's how they sell it to the Congress. Because Congress at the end of the day is really the one deciding whether or not NASA should spend $1.2 billion on a mission. And so what I'm going to show you now is the simplicity of how NASA works when it comes to the science question, and how you look at the big picture question, and then based on that, you come all the way to even figuring out what are the screws that you're going to use for your entire spacecraft. And that's really what we're trying to show here. So in terms of science requirements, that's what the scientific community focuses on. So when you look at what NASA cares about, is that they have this criteria called the mission evaluation criteria. There's the baseline mission requirement and there's the threshold mission requirement. Can anyone guess the difference? Obviously the definitions are there, but the difference between a threshold and baseline? Please.
What you need to get the program like going, and threshold is what you need to actually start building the thing and to get the contracts.
Close. Yeah, threshold is something that you absolutely must have. So the bare minimum for a mission to achieve its objectives. And I'll talk more about that too. So that means if you have anything less than that, you're not going to really be a successful mission. Whereas baseline is, what if I had the money to really do what I want to achieve to the best that I can? And it's always subject to change because as we learned this week, one of the missions that I was a member, GDC, or the constellation of satellites going to orbit, it was put on pause because the presidential budget was not sufficient enough to actually have the mission move forward at this stage. So, and that's why it says it's subject to change, because, you know, the scientists are always, you know, they got plenty of science questions that they would love answers to, but it comes at a cost, because you're on a spacecraft, fuel, mass, and power budgets are really critical. Therefore, you're trying to figure out how to minimize risk while keeping your main objectives afloat. So when we look at the mission success criteria, that's again something that now this comes after the mission has flown, because then that's really how NASA looks at things, because they give you the money, you go do it, and then come back, they ask you, was it successful or not? And you have to show them whether or not the mission was successful. And the way they do it is that I'll show you exactly how they do. They have exact definitions before you go and give you permission to fly. They tell you exactly what those conditions are, and then come back a few years later, if not decades later, to report whether or not the mission was a success. Are there really consequences with a lack of success? That's for you to decide. But at least they can call it a success or not. Okay, so I will not really go into reliability much, but the only thing that I'm going to point out is that redundancy is key for a space mission. And I'm guessing you all can tell why, because you know you're sending a lot of money, you're investing a lot of money into a spacecraft, and redundancy will make sure that if one instrument went bad, the science objectives that you have can still be answered by other instruments, because you don't want to be bound by a single point of failure in case like one screw fell off and all of a sudden the entire mission is no longer in operation. And so except the only thing to keep in mind when talking about redundancy is that it's nice to have two of each instrument on board too, because, you know, why not? However, there are two constraints to always keep in mind. And that's really the key here, is that we always do a trade study, is how to get the most out of the resources provided. And a spacecraft is the very good example of that. And if you have any questions, please feel free to ask. So here are the very simple science objectives that the entire mission was based on. The community decided that there are 3 objectives that are so critical to know the answers to that is worth investing so much money. And it started in the 80s and it finally flew in 2018. So that shows you that how long a typical mission takes time to actually come to fruition. Because you have to sell it to the community first, then sell it to NASA, and then NASA sell it to Congress, and then provide you the money. That's another decade of now building it, and a decade in some cases to actually get there to do the measurements. So it's fun. So the number 1 question is to determine the structure and dynamics of the sun's coronal magnetic field, because we can always observe it from afar with telescopes, but we actually don't know the structure up close. Because, and I will show you later on some scientific discoveries that is really the result of us being in the solar wind very close to the sun to actually, touch the magnetic fields and see what they're all about, what's in it, and what do they tell us. And then after that is what you pointed out, is to discover how the corona and solar wind are heated and accelerated. So because there's this thing called the coronal heating problem. I don't know if any of you have heard of it, is that the solar atmosphere is a lot hotter than the surface of the sun. And no one still knows why. Because typically, if you're a black body radiation, the surface is the hottest, and then after that is a function of 1 over r to the power of 4th, right? So the power is going to quickly drop. But that's not the case in the solar atmosphere. And we still need to understand why. And I'll show you a few results that may pique your interest. And then finally, the idea is to understand how energetic particles are produced and evolve. Because these energetic particles, even though they only propagate along magnetic fields, when we have those very large coronal mass ejections that the video was showing, these come toward us and interact with the geomagnetic field, push it back, and in many cases, they actually expose our spacecraft and astronauts to these very energetic particles that can go right through you, and are very, very detrimental. So one thing, so now going back and talking a little technical, is that do you notice that none of these bold terms are things that you can replace with the word measure? Can anyone say why? And you can see every single word that you use in a proposal really matters. Please.
You can't determine. So you don't want to have a situation where we're going to figure out working. Or I don't know how to say it.
Yeah, so I think what you're trying to get to is that if you were to replace the word understand with measure, in this case, if you're not able to measure that specific physical parameter, then this entire objective is out. And that's exactly, so that's already 33% of your mission objective is out. So that's exactly right. So you use terms that does not, legally mean that you're gonna actually do just that. So that's really what it goes back to. So then after we look at the science objectives, again, which are the top 3 in these 3 sets, you see that we have, each of them has 3 science questions. So we break down each of the objectives into 3 science questions. And by doing so, we then start to get into the actual bolts and nuts of what are we really trying to understand about this question. So I'm just going to read a few here and there just to get a sense of what they're really trying to say. So earlier we had said that we're going to try to discover or trace the flow of energy to accelerate solar wind in the solar wind, or the plasma in the solar wind. So one question is, how is energy from the lower solar atmosphere transferred to and dissipated in the corona and solar wind? You see, this question now becomes very specific. It's something that now you can specifically answer that question, and then you can figure out what type of instruments you're going to need to answer that very specific question, right? So we started from the science objective, and I'll show you a decision tree in a second. So you start from the science objectives to give the community an understanding of the big picture of the mission. Then science questions are exactly what the scientists are going to look for and try to answer. And then after that, we go into the success criteria. So I go back to the term success because it's not just about the instruments or the spacecraft getting to orbit and exactly to the location that you want. You still, that has a purpose. You're trying to figure out exactly what is it that we were here to achieve, right? It's just like going to grocery store, getting to the parking lot and coming back. Or in this case, just leave the car and walk back because this spacecraft is not coming home. So now what you need to pay attention to here is that how the community actually defined what success would look like for Parker Solar Probe. So in this case, there is a level 1 requirements for the mission. And that means that at least 2 of the 3 science objectives have to be answered. Okay. And what does that mean? That means that earlier I showed you 3 objectives, 1, 2, 3. It says that at least 2 of these have to be addressed. And then of the 2, or in other words, at least 1 of 3 sub-questions for a given science objective needs to be answered for that objective to be successful. Do you see how already it's going from answering all of these science questions down to if you just answer 1 of these questions, you're addressing that objective, right? Because the chances of failure for each of these instruments, we're talking about, millions of degrees, very close to the sun, and we're trying to understand what is it that we can very comfortably answer here in order to make the mission a success. Because if they don't, then the next time Congress decides on their budget, they're going to reconsider exactly how much money they should be receiving. But that's not the only thing. So we talked about all of the, science objectives and then science questions, but there's also another thing. Here, we're talking about the amount of data collected on the spacecraft. In this case, 64 gigabits. And then this is another, so we talked about how close to the sun you need to get. Here's exactly how it's spelled out. You have to have at least 150 hours of data below 20 solar radii. Okay, so that means you have to, 1, get close enough to the sun. So you're within 20 solar radii from the body. You have to be able to handle the heat. And this is not something that just constantly orbits the sun. It goes back out and come in. And so you have to spend enough orbits, bless you, close to the sun to have 150 hours of data from that environment. Not only that, you also need to get a lot closer, 10 RS or solar radii, and have at least 5 hours. So if you can just finish 1 orbit very close to the sun to have enough data to send back, that's called mission success. And all of these are required for the mission to be a success. So you see, all of a sudden, a scientific space mission is no longer just about the science, is it? It's about the amount of data. It's about really what you try to solve Congress on, which is distance, which we've never been to, and a lot of other politics. So now what the next step is, so we looked at the science objectives, we talked about the science questions. Here, we're trying to show exactly what type of instruments you need to address each and every one of those questions. What instruments are required, for example, to answer question 1.1. And so here's a list of all of the instruments, their dynamic range. These are the absolute requirements, but so you have, again, just like the mission itself, you have a baseline value, what's nice to have, what type of resolution would you ideally want to have, and there's threshold. That means that if I want to answer this specific science question, what do I absolutely need to measure, right? So for example, do I need resolution lower than 1 second? Do I need a telescope that has a certain type of view of the sky or field of view? So that's really what comes out here. And FOV is field of view, as I'm sure all of you know in this club. So here is a very simple matrix that really shows. So we just looked at the list of instruments, and here, again, the 3 science objectives, each of the sub-questions from the different objectives, and then here is showing exactly what instruments are absolutely necessary to answer that specific question. You see, it's already becoming just a game of just point matching instruments with science questions. Because when NASA tries to look at your final results, they're not going to sit there and prove whether or not your articles actually showed what you say they did. They're going to go to the community and see whether or not, one, did these instruments work? Did they send back data? And if so, were they able to answer those questions? So that's how they're going to look at it. So for example, in order for us to determine the flow of energy from the corona and solar wind, we need to measure the solar wind plasma. We need to know exactly what the field lines are along which these plasma are propagating, and we need to measure plasma waves because plasma waves are responsible for heating plasma. So and many others. So now the other aspect is that earlier we talked about the single point of failure, which means that if one instrument goes out, see what happens. If one instrument goes out, let's say this instrument goes out, do you see how many of the science questions all of a sudden become obsolete? It's no longer so. Only 2 of the questions do not rely on plasma measurements. Okay, so if that instrument goes out, it's already a single point of failure. Why would NASA allow something like this? And that's what this chart is about, is that those are only your primary instruments. But we have shown that with the same instruments, you can also do secondary measurements to achieve again, to measure those physical parameters in other ways. So for example, instead of directly knowing the plasma density, you can look at their emission from the plasma to understand what the plasma density was. So you can see, for example, if the electrostatic analyzer goes out, you have at least 4 other instruments that they do measurements that you can translate in a way to answer those type of, or get the type of measurements that SPAN could. Yes.
When they have the idea of
That's exactly right. Yeah. Even though when the announcement comes out, announcement of opportunity, or AO comes out, different teams respond to the opportunity separately. And then NASA goes ahead and picks only 4 instruments in this case to be part of the mission. Until then, the community has already determined what do we want to measure and how do we want to do it. From thereafter, once they've been picked, now they are required to work together on what we call the science traceability matrix, is to exactly map these out. Yeah. Great question. Okay, so how many of you have heard of the fault tree analysis? Yeah, excellent. So there's plenty that I'll be talking about here, but the whole idea of this is that, again, I want to just show you how an administrator at NASA determines whether or not a scientific mission was successful or not, because not everyone has a scientific background at NASA. I don't know if you knew this. So I'm sure many of you, if not all of you, have know about the logic gates. So when you look at something like this, would someone would like to tell me what that is trying to say?
That's saying the loss of instrument A or the loss of B would result in a failure of that particular.
That's exactly right. So yeah, that's exactly. So if one goes out, do we fail? So how about this? Someone wants to try that? Yes,
Out, then it is the end result.
exactly. So they both need to go out for it to fail. And then this is oftentimes new for the audience. Have you seen this type of gate before? Can you interpret what that means?
So 2 out of 3.
Yeah, exactly. So at least 2 of the instruments have to fail for this to fail. So why do I show you this? I'm going to go back to my science objectives. So here are the 3 science objectives. What is this saying?
2 out of 3 fail, it's a failure.
That's exactly right. Just like the words had spelled out, now you're using the gates to indicate the same thing. But typically, the scientific community, if when you ask them, they're going to only look at the mission as just this. They don't realize that there's so much more that engineers have to worry about, not the scientific community. So a very good example is we already said how much data you need to collect at 20 RS and at 10 RS. So those are also equal important. And as you can see, the size of this is a very politically strong statement too, is that this significance of your science objectives is equal to other squares here. Nothing is really changing. So this is really trying to show you that for a mission to succeed, every single one of these has to succeed. And so when you read this, can you tell me what that is trying to say, this gate here? Is it the and or?
Looks like
That's exactly right. Succeed. Yeah, exactly. So even if one of them does not succeed, the mission is not a success. So that's the only way to keep the PIs on their tiptoes until the very last day, until the measurements are done. Okay, so now let's look at this set of instruments. So clearly we have 9 different instruments on board, or sets of instruments. And this is indicating at least 3 of the instruments need to fail for the mission to fail, right? And I'll show you exactly how that would work. And it really goes back to that earlier table that I showed you over here. So if 3 of the 9 instruments, these are suite of instruments. Inside of them, there are different sensors. If 3 of those go out, practically you get to a point where you cannot address 2 of the 3 science objectives. So now let's look at only one of the objectives. So in this case, objective 1, we have question 1, 2, and 3. All of a sudden now this went from a OR gate to AND gate, which means that you have to lose all 3 of them for that objective to go out. But because if you remember in words, we said that if you can answer only one of the 3 science questions, the mission would still, or the objective is still met. So in this case, in order to answer question 1.1, you need plasma data, you need magnetic field data, and you need plasma wave data. And for, in this case, any of them that go off, you cannot achieve the answer to your question. So, but that's only the primary instrument. In this case, now it's showing that, yes, it may be true that if you lose sensor X, you may not be able to answer a specific question, but then we also have the secondary instruments as backup to help us further ensure that we can actually answer a question. And I'm not going into the details because I don't want to bore you with the individual sensors. So I want all of you to look at this chart and tell me what is so wrong about this chart. If this is true, why was this mission? Can you identify a single point of failure here? You didn't think this was going to be an easy talk, did you?
Fields E. Fields E.
Yes, what about field E?
Well, if field Z goes out, use 3 measurements that fail, and that wipes out your mission.
That's exactly right. So the top gate is saying that if 3 of these instruments go out, the mission is a failure. And so if you look at the electric fields, which are here, here, and here, it's enough for all these 3 to go out. So why was this allowed? The answer is that the electric field sensor itself has many, many, many subcomponents. The whole instrument is not going to go out because just that electric field instrument has many, many, many other components inside. And all of them have to, as you can see, all of them have to go out for that instrument to no longer operate. You see, so if I go back all the way to this slide where we had the science objectives, now you're seeing how this is spreading into many, many, many subcomponents. So this is, at this point, we're at the sensor level. And then finally, so after applied physics lab, which was the Johns Hopkins University that really ended up building Parker Solar Probe, went through the entire fault tree analysis, looked at every single choices they've made for the instruments. They actually came back and found that there is a single point of failure. What was it? It's actually in the electronics box. One of the capacitors they're using on this board could be a single point of failure. NASA sent it back, they replaced it, and that's how they got rid of every single possible point that could go wrong for the mission. Yes.
Was it like the power was going through the single capacitor and they added multiple?
I don't know the details. Good question though. So yeah, so that's how really engineers and scientists, which can't really often see eye to eye, communicate. Because scientists always want everything and engineers are always, nope, you can't have that. Let's be more reasonable. So yeah, so that was pretty much the background that went into designing a mission based on very simple science objectives. And then so now NASA is trying to again paint out that exact same fault analysis tree for the interstellar probe, which is going to take at least 50 years to even get to its point. Or stay in orbit for 50 years, and just think about how massive that fault analysis tree is going to be compared to one probe with 4 instruments. So now here are 5 new discoveries done by Parker Solar Probe. Also, I forgot to mention that the first video pointed out that Eugene Parker is where the name for the mission came from, and at the time it said it was a living scientist. Dr. Parker has passed away the year after the mission was launched. So he did get to see the launch, but not quite to see the final outcome of all the results that have come up. So here is, if now that you did all these engineering work and went through the entire practice, what can you really achieve with a mission that can go so close to the sun?
Traveling through the sun's blazing hot atmosphere, NASA's Parker Solar Probe has sent back a complex, close-up view of our star. The spacecraft confirmed that our picture of the sun from Earth is deceptively simple. Parker is the closest spacecraft to the sun, meaning we now have never-before-seen details about the solar wind and solar energetic particles. Solar energetic particles are high-energy particles that can endanger both astronauts and satellites in space. The solar wind is the continuous outflow of particles and magnetic field from the sun. Both speed out, filling up space and affecting space weather throughout our solar system. For the first time ever, we were able to go to the source of the solar wind and solar particles. Here are 5 features Parker saw. We've long known that space is full of cosmic dust. We can even see the dust from Earth because it reflects sunlight. Parker saw evidence that the dust stops at an estimated 3.5 million miles from the sun. As the dust gets closer, the sun vaporizes it, creating a dust-free zone surrounding the star. At Earth, it appears that the magnetic field lines flow evenly out from the sun, but Parker saw them behave in a surprising way. The magnetic field lines flip in a whip-like motion, turning 180 degrees around in a matter of seconds. These switchbacks came in clusters and were timed with fast-moving clumps of plasma in the solar wind. Scientists have long wondered if the solar wind is generated as a continuous flow or in spurts. We now see evidence that the solar wind has rough, irregular texture. The plasma within it also seems to lack an orderly sense of direction. Some clumps of solar material fire out into space, while others fall back toward the sun. These clumps may be distorting the magnetic field, causing the switchbacks. They may also be an indicator of what the solar wind looks like in its early stages after its birth on the sun. Parker found a transition point in the solar wind. The corona is the sun's faint, outermost layer that transitions to the solar wind. Before Parker, scientists knew that the corona rotates with the visible surface below it, but they didn't know how, or where, the solar wind switched to flowing straight by the time it reaches Earth. Parker has finally spotted signs of this transition, and the changeover happened significantly farther out than expected. Although the sun has been very quiet over the first two orbits, Parker observed several tiny bursts of solar energetic particles. While these events have been seen before, never ones this small. The fast-moving particles from these modest bursts spread out as they move from the sun, making them undetectable from Earth. Without Parker's front row seat, we would never know that the sun is regularly producing these small-scale events. Fast-moving particles are a source of dangerous radiation. The more we learn about these eruptions, the better we can protect our technology and astronauts. Parker still has more work to do, but it's already helping us see our star in a whole new light. Traveling through the sun's blazing hot atmosphere, NASA's Parker Solar Probe has sent back a complex, close-up view.
So yeah, you saw that the 5 new discoveries could have only been done if you were in the environment that Parker Solar Probe was able to reach. And so this last bit is about getting finally to the solar corona for the first time by Parker Solar Probe. That's something that has been a dream of many solar physicists for a long time, and it only was achieved 2 years ago.
So it actually touched the corona?
It touched the corona for them. That's really what this is about.
Liftoff of the mighty Delta IV Heavy rocket.
In August 2018 in Cape Canaveral, Florida, NASA launched Parker Solar Probe to touch the sun. After spending a few years spiraling closer to our star, the spacecraft has finally arrived.
It's amazing. Parker Solar Probe is touching the sun.
This is Noor Rawafi, the project scientist of the mission. He has been waiting for this moment since the beginning of his career.
This is a dream come true. One of the major goals for the Parker Solar Probe mission is to fly through the solar corona, and we are doing that now.
So what does it mean to touch the sun? To answer that, we need to look at the sun's structure. Unlike Earth, the sun doesn't have a solid surface. It's a giant ball of hot plasma that's held together by its own gravity. Solar material flows out from the surface, but around the sun, it's bound by the sun's gravity and magnetic field. This material forms the sun's atmosphere, the corona. Eventually, some of this hot and fast solar material escapes the pull of the sun and gushes out into space as solar wind. The boundary that marks the edge of the sun's atmosphere is known as the Alfvén critical surface. We didn't know exactly where this boundary was, but for the first time in history, a spacecraft has crossed it. Parker Solar Probe ventured into the corona, touching solar material still bound to the sun. The wispy corona is too faint to see most of the time, but it's revealed during total solar eclipses. For centuries, we've been studying the sun's atmosphere during eclipses because it's important for understanding how a star influences life in the solar system. But much about the corona remains a mystery.
Two of the most challenging scientific mysteries in astrophysics occur in a region that we call solar corona.
The first mystery is about the temperature. The corona is about 300 times hotter than the photosphere, the visible surface of the sun below. Secondly, there's a constant stream of particles flowing from the sun known as the solar wind. It accelerates up to millions of miles per hour out of the corona, and we don't know how. Solar wind can disrupt our satellites and technology. To better protect them, we need to go where the solar wind starts, in the corona. So heading there has been a key goal of NASA's for a while. We first proposed the idea of sending a spacecraft to the sun in 1958. We didn't have the technology to withstand the journey until the 2000s. Since its launch in 2018, Parker has been heading towards our star. Then, in April 2021, during Parker's 8th orbit around the sun, the spacecraft was around 20 solar radii, or 8 million miles from the sun's surface, when it crossed into the corona.
This is a huge milestone. It took us over 6 decades to come to this point.
As Parker entered the corona, its whisper instrument took these images. Streams of plasma surrounded the spacecraft, and Parker's other instruments detected that the magnetic conditions had changed. Outside the corona, solar wind gushes out, pushing solar material away at high speeds so that it can't return back to the sun's surface. Inside the corona, the sun's magnetic field becomes much stronger. Solar material is slower and tethered to the sun. Instead of a smooth divide, Parker found that the boundary between these two sides is wrinkly. These bumpy ridges are created from huge flows of plasma traveling out of the corona. Scientists are not sure why this happens, but as Parker gets closer, we're finding more clues. Before entering the corona, Parker had seen kinks in the solar wind where it would momentarily double back on itself. Scientists called these features in the solar wind switchbacks, but no one knew how or where they formed. In 2021, the spacecraft finally tracked switchbacks to one of their origins. As Parker got even closer to the sun, it detected bursts of switchbacks. Scientists traced these bursts all the way to the visible surface of the sun. Here we see distinct cells. As heat rises beneath, these convection cells churn and create funnels of magnetic energy above the surface. Scientists found that switchbacks form inside these funnels before rising into the corona and beyond. This is only one piece of the switchbacks puzzle though. Exactly how they form is still unknown. Over the next few years, Parker will keep looking for clues as it explores our sun, the only star we can study up close. The sun is also the only star known to support life. So understanding it is critical as we search for life beyond our solar system.
That will link directly into the question, are we alone in this universe? And that is one of the biggest questions for humanity to answer.
Yes. We have a question from the chat from Ken Cook. Probe, aiming a radio dish at the sun is normally a really bad idea.
That's a very good question. So you may have noticed that the orbit again is not circular around the sun. It comes back out to the interplanetary environment. That's where it dumps the data before going back to the sun. Yes.
But then when it is closer to the sun, is there any kind of, I guess, like low
data just to say, hey, here it's in the correct orientation, systems are nominal? Does it have anything like that?
That's a very good question. I don't know the answer to that, but it makes a lot of sense to have some critical information sent back. I don't know the answer.
I did a yeah, yeah.
It hasn't. It's still in the 15s. Yeah.
Well, that answers my question. Is the mission over?
It's not over. And I like that you all know already what's required of the mission. So if I don't know how much, if I have any time left. So you saw that the switchbacks are critical piece of this coronal heating problem puzzle. Yes.
Question. Probe flies close to the sun before the instruments are destroyed, or are we going to try and get it back?
We're not getting it back. It's burning in the solar atmosphere. Yeah. As soon as it runs out of fuel, it no longer can fix its momentum, therefore rotating and therefore melting everything behind the heat shield. Yeah. Yes.
I don't know if. Guess they need some kind of RCS for count, but does it use reaction wheels or?
Yes. Yes, absolutely. Yes.
It's question time. This primary goal of understanding how the heat is generated and then accelerated into
Yes.
primary objective met, and do we? Well, that happens, and will it be important, even politically? To understand how things like the Carrington event might happen and how we might protect the earth in future generations. Could you leverage something like that for future?
Absolutely. I couldn't have asked for a better transition question. So let me answer that question in my next slide. So I personally study the switchbacks. And if you recall, switchbacks are those little kinks in the magnetic field very close to the sun that comes out of the corona into the solar wind. And just so you know, this is a very bold statement, but we were able to finally publish a paper with that title. So why is that significant? So this is what a typical switchback looks like. These are magnetic fields with a little kink in them. And the reason this kink is so significant is that it's very unstable for a magnetic field to have a kink like this, because as this is building up magnetic energy where it does not belong. Okay, so for a typical system, the ideal thermodynamics requires that it goes towards relaxation. This is not a relaxed state. It has to release its magnetic energy. So why do we see these switchbacks, and what happens to them over time and over distance from the sun is something that we still need to understand. But so I will not go into the details about any of those, but the one thing to point out is that, so the field lines are in orange. And so these are the pointing directions in the magnetic field. So what you notice is that your spacecraft sees that the field lines are pointing down in this case, and then all of a sudden the magnetic field is pointing up and then again down. Okay, so that's how, when you look at those wiggly lines, you just look for when do you cross zero and come back up. Okay, and then you look at other parameters such as the velocity of the ions or other particles, and then electrons. So the green little dashed line is the spacecraft trajectory. So it's going through field lines that don't have any particular structure. All of a sudden it sees that the magnetic field flipped. And that's how you understand that, oh, there is a switchback in the solar wind. And so switchbacks have been observed as far as 1 AU by other missions, including Helios, right? So Helios and Ulysses, especially Ulysses, was out of the ecliptic plane. It would go over the poles of the sun, and that's how the orbit was. And as soon as you get away from the ecliptic plane, the solar wind velocity significantly increases. And so one wonders whether or not the reason these switchbacks are observed farther from the ecliptic plane is that they're coming at you faster. Therefore, if they were to evolve, they haven't evolved enough yet compared to in the ecliptic plane, where they may have disappeared by the time you see them at the same distance from the sun in the slower solar wind. So here is a typical wiggly line. These are all magnetic field components in normal, rotational and tangent, radial, normal, and tangential components. And so the component that we care about is the radial one, because all the field lines from the sun are all going straight out. And then if you want to see a switchback, clearly you're gonna have to see a quick return back pointing toward the sun and then out again, right? So when you look at these black or blue line, you see that there's this all negative, 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 and all of a sudden you cross zero, you stay positive, and then come back to negative, right? So in this case, this is exactly what we mean by switchback. And in our study, we broke down the switchback into 5 different regions. The leading regions, which are quiet, and the transition region. The transition is sandwiched between the spike region. This is the spike region where the magnetic field has completely changed sign. And then the same thing in the trailing part. And normally the leading part of a magnetic structure is more substantially important because that's the side that is ramming into things, is interacting with the environment in front of it. Therefore, we focus our entire study on this region alone, as I will show you. And so what we did is that luckily God created undergraduate and graduate students so you can have them look for events. So students helped with finding nearly 3,000 switchback events in 8 Parker Solar Probe encounters, of which only nearly half had quality magnetic field and plasma data, or just magnetic field data. And then we run it through a specific analysis where we're looking at the orientation and dimensionality of the structures. Is it 2-dimensional? Is it 3-dimensional? That's really what that analysis is. And from that, we only are left with nearly only 1/3 of the events. And that's the distribution of the events that you're looking at here. So here we're breaking down in things in terms of the normal component of the magnetic field. So the normal component is when you have a discontinuity. So think of it as you have a surface or a gradient in a certain physical parameter. So everything is of the same environment. All of a sudden the environment changes. That's a discontinuity, right? And that discontinuity oftentimes has a normal component, which means that a component or a unit vector that defines that surface. So, for example, at this surface, this is the unit vector. If it was pointing this way, the unit vector would be pointing in a different direction. So that's really what that is trying to show, is that the relative jump in that normal component compared to the total magnetic field. And in this case, the difference between the jump relative to the leading quiet region. So anyway, so what's really important about this specific observation is that here we're looking at the tangential discontinuity and rotational discontinuity. And that's really 2 types of discontinuities that determines whether or not plasma and matter are allowed to propagate through the discontinuity or not. And the reason that's important is that if energy is allowed to propagate a certain discontinuity, that means it can help with the relaxation of the discontinuity, and over time it gets rid of it. Whereas if it doesn't allow, that means that discontinuity is going to continuously stay in the solar wind and just propagate, right? So that's really what this is trying to get to. So one of the main things that we quickly discovered was that as we look at more and more data coming closer and closer to the sun, which all of these different bins are showing the number of switchbacks inside of each of these radial distance bins, we found that when we look at the ratio of the number of rotational discontinuity to what we call either type or tangential discontinuity, it significantly drops as a function of distance. And the drop is actually has an exponential fit with a half-life, because that's how you study physical phenomena. Exponential distribution, you quickly look at the half-life to see if something was to naturally evolve, how quickly would this rotational discontinuity evolve to that tangential discontinuity. And we came up with a number 8.7. And I'll come back to this, why that number is so significant.
Is that in layman's terms saying?
That's exactly right. That's exactly right. And if so, where's the energy going? That's
We couldn't
exactly-
hear the question, actually. It cut out a lot.
Yeah, so the question was, does this in layman terms mean that the rotational discontinuity type switchbacks are dissipating with distance from the sun? And the answer
you.
was yes. Yeah.
What's a dissipative event versus what's a non-dissipative event?
So dissipative event is where you over time
No, I know. I'm saying you're trying to distinguish between all the data. You want to find the ones that are dissipative versus non-dissipative. You know, you ignored the non-dissipative ones in your data original data set. That's how you
so that's
focus
actually
down onto the right one.
right. So I wish I had the capability to do something like that. So here, one thing you need to remember is that this is a single point of measurement. That means the spacecraft only, so these structures are moving so fast that we always assume that the spacecraft is stationary. We've never had a spacecraft moving so fast. Still, compared to nature, we're nowhere near the same velocity, right? So we always assume that the spacecraft is sitting there and the structure is moving over us. And so that means that when we see a structure, we will never see that structure ever again. So when we try to study evolution, we can actually stay with the same structure and move with it and see how it evolves. What here you're looking at is we're looking at 1,800 events and making assumptions that when you look at it statistically, it's showing what the behavior is. So here, I think one thing, and that was a very good question you just asked, is that we cannot distinguish between dissipating versus non-dissipating. Here, we're only saying that if they're evolving at a rate with a half-life of 8.7 RS based on statistical results. If you want to know the answer to that specific questions that you just asked, then NASA needs to launch more than one probe to orbit. So you go and convince Congress. And they have to be radially aligned at different separations from the sun or distances from the sun. So the other observation was that when you look at the leading parts of the switchback, the quiet part, the transition, spike, and the trailing parts, transition and quiet, you see that when you look at the magnetic field, which is red, it slightly drops in the spike region. So magnetic field is only very slightly changing, not very much. But when you look and plasma density is slightly more. But when you look at the velocity, which the reason we call it the spike region is that, you know, plasma velocity is increasing. So we expected this. But what's really substantial here is the temperature of ions. You see how significantly they're jumping inside the spike region compared to the typical background solar wind. That's one of the key features here. And now, because we're including plasma, we're down only to 500 switchbacks from what you started with.
Region, is that turbulence or is that?
So that's the area where the magnetic field completely rotates and stays there until it's after the, yeah. So the transition region is that turbulent region between where you go from quiet transition into the spike region. Yes.
Video it mentioned. Do they vary a lot, or is it almost always like 2 to 3? Or like
2 to 3.
time?
Yes. So even the switchbacks themselves, they go anywhere from few seconds to few hours in duration. And the video also mentioned that they come in patches. So you're not seeing any switchbacks. All of a sudden, you see the whole load of them coming at you at once. So we're still trying to understand exactly why those happen. And there are many theories, and there are many camps of scientists believing in each of the theories, and I've got my own. So yeah, so this is really the $1 million plot, because what we're trying to show here is that, and this is an older version of the plot. What we're showing here is that when you look at the tangential discontinuity type switchbacks versus rotational type, magnetic pressure, or the amount of magnetic energy stored in a rotational discontinuity type switchback, which is a lot more abundant closer to the sun, is 64% larger than tangential discontinuity. Okay, so what that plot earlier was showing was that these rotational discontinuity type switchbacks seem to be disappearing as they go away from the sun. Potentially means that they're becoming more tangential discontinuity like. And this plot now is showing that if that is so, that means they're losing magnetic energy. Okay, because they're losing 60% of their magnetic energy as they go from, if they go from rotational to that tangential type discontinuity. So now this is how we put all of these different observations together. So the first one was that there seems to be a lot of rotational discontinuities, rotational discontinuity type switchbacks. And one of the mechanisms that can generate that in the solar atmosphere is magnetic reconnection. And what is magnetic reconnection? Magnetic reconnection is the process through which field lines that are oppositely pointing. So think of it as these two field lines pointing in different directions coming in contact, they try to cancel each other out. But that's explosive process because it heats up plasma very much because all of that magnetic energy now all of a sudden has to go somewhere. And that somewhere is the kinetic energy of the little charged particles. So that means that there are open field lines on the sun, and that's, we're still trying to understand what an open field line looks like, because physically speaking, we all know the Maxwell's law, you can't have open field lines. If that means that you have divergence, and divergence of magnetic field has to be zero, right? Based on simple Maxwell's law. But come to the solar physics community and we have open field lines. Okay, because we just don't know where they close, how far they go before they close. So we call them open field lines. And we also have closed field lines that was showing in the video, very close to the sun. These are very strong magnetic fields. And so as soon as these open field lines and closed field lines come in contact, then you start to get these reconnections. So this blue line used to be an open field line that touched a part of that closed field line with different polarity. It reconnected and then caused the formation of this switchback. And as this switchback moves away from the sun, it's so over here, it's a rotational discontinuity type structure. And as it's propagating, it's becoming tangential. And along the way, it's losing 60% of its magnetic energy to what that number that I pointed out earlier is losing all of that energy to the solar corona environment, because that number is below the critical Alfvén surface that we talked about, where the energy of solar wind is deposited before it becomes accelerated to reach the interplanetary medium. So our argument is that as these switchbacks are generated in the solar atmosphere due to reconnection, this is a massive argument that many do not believe in. So just getting that across was already challenging, because some say that it's generated in the solar wind, some say it's simply just due to turbulence. We're saying that it's due to reconnection, and this has been an argument for a long time, and it's not going to be resolved anytime soon. It's just they say the scientific mind never changes, only the old scientists die. That's how progress happens in science. So we'll see what happens to this theory. So now the idea is that these switchbacks are depositing so much of their magnetic energy in the solar corona, hence contributing to the coronal heating problem. 16% of that energy that is coming from the magnetic field is going straight just for this transition from this to this within the critical Alfvén surface. So that was the study that we published that was in the astrophysical journal letters last year. So yeah, so the questions that remain now is, are these true, what we discussed? And now that Parker Solar Probe is going actually inside the solar corona, are we going to see switchbacks that continue this trend, or are we going to see something different? Because if you notice, and that's not what scientists normally show you in their data, is that there is a peak in our data that we conveniently didn't talk about. And that's because it could be that the actual source of tangential rotational type discontinuities is actually somewhere around 35 RS. It doesn't have to be all the way to the surface of the sun. But the only way to know that is that we go closer to the sun inside the critical affluent surface and actually measure these switchbacks to see if their behavior is any different. And so the video already indicated that there are switchbacks in the within the critical affluent surface. So the source has to be somewhere there. But what is the source? It's yet to be determined. And that is all I have for you tonight. Any questions? Thank you. Yes.
I didn't understand when he talked about the granulation of the sun and that were generated right there.
Yes.
I didn't understand that.
Yeah.
That happened out in the corona. This is down on the surface of the sun.
Right.
Rating.
Yeah. So absolutely. So when you think about those dark spots on the surface of the sun, sunspots, those are the regions where you have open field lines coming in contact with very strong closed field lines. And when we see switchbacks are oftentimes at those transition regions, which could be exactly where these two come in contact. Yes.
I'm just curious, like currently, how much lifetime they have? Because obviously,
You're really concerned, aren't you? You want your money worth.
obviously, the more power you burn, you get, but also so correct.
It is using gravity assist, by the way. Venus is how it's doing it. Yeah.
So, what is? I was wondering if you knew, like, is there?
We don't know. And that's the reason for that is NASA never really designs and builds a mission that lasts for a very specific time. It's always like when you think about Voyager was supposed to last 10 years. They're going after all the scientists right now to come get all these magnetic tapes and get the data out of it so that this community could use them, right? Scientists that have retired long ago. So the answer to your question is that we would only know based on the rate at which fuel is being burned.
Has anyone done that calculation?
I'm sure they have. Yes.
You get those data.
It's on average, if I'm not mistaken, it's around 2.5 months or 3 months that you go to Venus, come back out. Right now we're at orbit 13. So you do the math, 2018 to 2023, 5 years divided by 13 divided by 5. Those number of months. Yes.
You get through all. Data charts.
Uh-huh.
It takes a while to build a piece of equipment.
Yeah.
First, you gotta get through everybody arguing about what I get and what you don't get.
That's very true. So there are two types of NASA missions. One is that is led by the PI, which means that one person comes out and says, hey, if you give me so and so instrument, this is the mission that we're going to do. I'm trying to do one myself right now, the Swift. But this type of mission is where NASA puts together the science behind it based on the community input, and then they go after instruments. In that case, you somehow, try to get people get along, and at least, it's better to have something than nothing, because one theory over the other is going to win at some point. And I think over time we'll just they certainly are. And I wonder when they're always the oldest in the room, but yeah, that's always the case. That yes, there are camps where there are many theories about. We still don't know exactly how the granules that earlier we were talking about, how they're working, the rotation of the the material on the surface of the sun. And those are really what the entire process of the magnetic field formation and then rotation and all of that begins. We don't know any of it yet. These are all theories. So Solar Orbiter from ESA and NASA just 2020 flew is slightly farther away from Parker Solar Probe, but the beauty of that mission is that it's actually going farther from the ecliptic plane. The idea there is to look closer to the poles to answer some of these questions about how are these magnetic fields formed and what's happening to all these really hot charged plasma, because to your point is that all these theories have to be tested, because if we don't know the answer to those basic questions, the rest of the field is just hanging over, not much of a real foundation. So yeah. Yes.
What is that heat shield made out of? And two, has there been any instrument failure?
Great questions. There has not been an instrument failure that I'm aware of. Yeah. And the heat shield is made out of graphene. Carbon fiber. So yeah, and that's why the technology only came out in the 2000s, where you can have so much heat hit the shield that does not melt.
And is it deteriorate?
No. Well, the front does, but they have 4 layers of it. It's separated at a distance. Yeah.
Any questions from the Zoom audience? No. I can't believe it's not asking anything. Do they?
Don't encourage them.
Well, we can hear it, but the problem is the speakers who are in the room, other than our main speaker, keep cutting in and out. So we have not been able to, the recording won't show what the questions are that he's answering.
I'm very sorry.
Well, it's not your fault. It has to do with how the room is set up, and it's a problem that we've had in the past.
Yeah.
We all the happier that we're moving to Detroit.
Were there any questions that you did not get the answer to in the chat?
Your presentation has been very fascinating, and it's intriguing given the fact that you really only have one point. You're able to think,
Questions in chat.
suppose that there's really complicated twisting of all of those things, because you're just taking this one little sample as you're ripping through the corona and through those fields. And you're trying to imagine what this huge 3-dimensional structure looks like based on that one thread.
That's exactly right. Don't I deserve a bigger salary?
Can you say magnetohydrodynamics? That's really the whole point here.
And that's a hot subject.
It is. That's so true.
Okay, if there's no other questions, I'd like to thank Mojtaba. Appreciate it.
Thank you.
So as a small token of our appreciation, we like to give our guest speakers a club T-shirt, or we also have some baseball style hats.
Perfect.
Would you
Are you
prefer
gonna ask my size in front of
T-shirt?
the
Or
audience?
they would look basically like this.
That looks great.
Okay, what size?
Large would be.
Got it.
Thank you.
Thank you.
Thank you all very much for the invite. Really, I had a lot of fun preparing and going over the slides with you.
Our treasurer that's got our shirt inventory is in Florida and coming back. I think it's next month
Now that
sometime.
begins.
So,
I'm not getting one.
no, you are. It's just, it's gonna be delayed a little bit. You'll have it just in time for warm weather.
Well, I don't think we've ever had a speaker that showed the process with the overlapping of the instruments and what would have to happen to make everything work.
Yeah.
If it's a spacecraft to just say, well, we have this magnetometer sticking out
Right.
here, and we do this, we do that with it, and that was, I mean, that's a nightmare.
And sadly, the communication between scientists and engineers continues to be a challenge for NASA to get across, because scientists always want the best instruments, and the engineers are always, are you considering mass or power or money?
And I thought your use of logic gates and showing what can fail and lead to success or not, and that was unique and very cool.
Yeah,
Really.
no,
Might give you a headache trying to put that together, but it was really cool.
It wasn't my work.
Yeah,
It's-
yeah.
it's
Yes.
But yeah, it's.
So apparently,
Yeah.
in science, engineers get a say. In the corporate world, engineers really don't get much of a say.
Make this work.
I
Make
think
this
something goes
work
wrong.
in the hardest way possible. Yeah, so we envy those.
Probably you should start shooting stuff into space once it's done. And then they can't change it once, once it's in space.
What happens is we shoot it into the world of commerce and it fails and goes down the moment we release it.
Well, then you would don't drop it into the sun, is what I'm saying. You're
Yeah,
at a disadvantage.
yeah, we're at a disadvantage. NASA versus trying to make the latest bank app work.
Yeah.
Yeah.
There's a huge difference in
So
where we sit in political stream there.
there is
So
one very good example of a single point of failure in NASA missions, and that's the Hubble telescope. The only, just you couldn't get a more obvious point of failure, and that was the lens. And that was the only satellite that we went back to actually fix it in orbit.
So that was amazing.
That will never happen.
And the way
again.
they figured out exactly what they needed for a corrective lens and
Yeah.
everything, that was amazing.
The number of,
that's the exciting part when you get together and figure something like that out.
yeah,
It's, you feel good about having figured it out, having the money for the mission and convincing the politicians that yes, we can fix it and yes, you want this data. Don't turn your back on us, please give us more money and
yeah,
use existing shuttle missions to be able to pull that off.
right, right.
So-
So there was this mission called Genesis. Went to orbit, the idea was to literally have just little discs come out, collect some solar wind plasma in the solar wind, and then close it, and the next one comes out, and just keep bringing samples back of the solar wind. This mission, when trying to return back to Earth, it could not stop. It hit the desert, shattered into pieces. But the logic behind the design of the mission was that all of these little discs were different thicknesses. So they knew exactly what, even in all of the debris, they could figure out what panel belonged to what science, what particles, and they still got a lot of science out of a destroyed satellite. So when you actually spend time on these fault trees, some good things can come out of it. Yeah.
Okay, draw.
Thank you. Get out of my high horse.
Wasted my time.
Okay. For the officers' part, I just have two things. One, I just wanted to announce again that this is our last meeting for the foreseeable future in Angell Hall, and next month we officially make the move to Detroit Observatory. Jeff and I are gonna work on some instructions on parking. There are actually several different options, but we'll put something together and send it out. I think overall, you're gonna find it's probably not that much more of a challenge than it is here, really, so. And actually, Jack, in fact, you want to explain what you found, Jack? That might help right now.
Well, I can, okay, I was out at the Detroit Observatory yesterday for Professor Seitzer's talk. And I wanted to find a place to park, so I did call up U of M parking. Guy referred me to a guy that handles all the parking problems. So, right next to the Detroit Observatory, if you go outside, you make a left and go west, a block down on Main Street is what they call the M86 parking lot. And I talked with the guys in that, okay. He told me 6 a.m.
What happened?
I have no audio or video.
Well, I can hear you and you can hear
Yeah.
me, but we can't hear anything in the room at the moment.
No, we can't.
Right as it was getting good too. It's like, okay, where do I park?
Guess we could have our own little meeting.
Well, I suppose so. Although some of what I had to talk about needed to be communicated to the entire group, but
Yeah, I assume we'll be back online in a few minutes.
yeah.
Yeah, a few of us have, yeah.
Why
A
don't
few
we
of us have direct messaged Jeff. So. Including you guys. Well, if it doesn't come back, my part can always be sent with an email, which is what I do a lot. So, in fact, I do it anyway because just to make it easier for whoever's taking the minutes, easier for them to just copy and paste. So, we may not come back.
We might not.
Well, it was an interesting talk. Oh, there's Joe.
Did some of the people get kicked out?
Well, everyone on the remote got kicked out.
I think it's the other way around. I think the folks in the room got kicked out.
Oh, well, yeah, because we're all on the meeting. And
yeah,
the meeting isn't.
Do we have to relaunch?
There's nothing we can do.
Yeah, we're still here.
They need to relaunch.
Yeah, the room needs to join the Zoom meeting.
Right, exactly. So unless you've sent them an out of band message, in other words, like, does anybody have his cell phone and can actually send a message to his cell phone? And will they pay attention to that? Otherwise, through the if you would DM them through Zoom, they won't see it because they're not actually connected to this conversation right now.
Good point. I guess that explains why
it didn't help any. Yeah, it didn't.
Yeah.
I mean, it fell on deaf ears essentially, right?
Yeah, exactly. Literally.
Well. So we need to out of band message them, something else.
Well, normally in the room, they can look at their screen and see all our little pictures.
That's assuming they're paying attention to it, but it's up there and somebody would actually have to be monitoring it.
Right.
And the people who normally monitor it are sitting in the Zoom chat.
Oh.
Speaking of
Yeah, hi,
single points of-
Jack.
What are there?
Your meeting has been kicked out of the Zoom.
Oh, you're not getting nothing?
We're getting nothing from you folks.
Okay, well. Yeah, we lost Zoom. They don't have anything. Jim Forster just called me up and he said they're not getting anything. Okay, they're trying right now, Jim, to find out what the problem was.
Okay, well, I'll hang up and hope for the best.
Okay.
Speaking of single points of failure.
Yeah.
Jim, can you hear me now?
Going through here,
That's fine.
because we logged off of this one.
That's right.
Remember, I had nothing to report.
Adrian didn't have anything to report anyway. You hearing things now, Jim?
Yes, well, I'm hearing you.
We're not hearing you, Jim, but we'll turn you up.
Okay, I heard Adrian.
Okay. So the only thing worth repeating then was in a presentation I did for the Warren Astronomical Society. I used your max reading of 21.99 in your SQM meter. And I
Okay,
averaged, I told them that's a real truly dark site, and I showed some pictures to depict how bright
through here.
the Milky Way is in different regions, not just in the core, but in the Orion region and all the dust lanes they can image it. Compared to the places that the was members had been to, where I was getting 21.2 and 20.5 and 20.9. And they recall it being this dark, wonderful place. But then I also mentioned since 2015, the sky quality meter numbers have been dropping to the point where we're 0.6 or 0.7, basically 7/10 lower than what it says on the dark sky chart where their data was from 2015. So we've lost darkness, even in places that used to sit portal 3 now sit portal 4. Some that used to sit portal 2 sit portal 4, depending on how far they're at the edge of portal. They're now in the middle of portal 4. As far as now, what you can get using astrophotography methods, you can still stack stuff and get a bright image, but if you use methods to get your images, you can then start showing difference, and even sky color will be different, detail will be different, and that's the aim of what I do with my images. I will mention, we're going back to Okie-Tex again. It's earlier, so it'll be hotter. There's the solar eclipses, annular solar eclipse, which will run down through Texas, and the total solar eclipse in 2024, which will run through Texas but come up close to us. There are a couple of towns in Ohio near Sandusky that are on the center line. And those are worth looking at. The media speaks of a big bright comet that will come in 2024. And I'm wondering why the eclipse doesn't garner more headlines. That's going to happen. This comet could be yet another sun.
They are more often than not.
Yeah, but so what grabs the public's interest can vary from day to day, but having something in the public side better than the public decide that aliens are invading, but that's just because Venus and Jupiter were close.
That's correct.
So
They're watching you.
yeah, we do know they're watching us, but we also know what it was, and several celebrities on Instagram posted that aliens are real, so any kind of media coverage is better than none at all.
Yep.
Yeah.
Yep.
So that's it for my report. Those that were on Zoom, I talked about doing a presentation Tuesday, Global Star Party, Wednesday for the Warren Astronomical Society.
Okay, thank you.
That's it.
Got it. Amy. Well, that was its brief escape. All right. Yes, thank you. Jack.
I did have some talk with this has to be the continued snow and power loss out at the observatory. I did go out there a couple times. I think the last I was there on the 11th. And I got to go there. Power was on the observatory. Everything was working inside. There's still a lot of snow on the ground. And there was a lot of different trees that were already knocked down, or branches, I'll say. Cecil Fernandez over at SCAS, she did send me an email that they were gonna cut some of it and clear the roads going up to the observatory and that. I'm not sure if that's completely cleared off right now. I think what's his name? Went out there, I think, today and looked at it, and I think moved some of the branches off of it and cleaned up some of the road.
Dimitri and I were up there today, and we've got the road clear all the way up, except there's a bank of snow that only a pretty decent four-wheeler can navigate just beyond where that fallen tree was that I sent the photograph of. The road to the observatory has some snow on it that again can only be navigated by a heavier vehicle. My Odyssey van certainly shouldn't try to do any of this, and it didn't. Which means we really can't be holding events up there right now. The other concern I have is that while we got everything that's down out of the way, there are a number of other trees that could come down any time, and until they're dealt with, I don't know how good an idea it would be to invite people up there. Something crashing and blocking the road in the middle of the night would not be good if there were some of us trying to return from an observing session. So hopefully by the time we have open houses, these things will be dealt with and won't be a concern. Certainly the snow will be gone. The immediate problem is I'm supposed to be taking the 17.5-inch telescope to Lake Hudson, but I can't keep it in my van for a month. It has to be immediately turned back to the observatory, and I can't get up there in my van. So the 17.5 might not be going to Lake Hudson this weekend. And then as far as the Messier Marathon goes, the only sure clear night is Sunday night. Since we can't use Peach Mountain, we won't be going up there. Saturday night it has improved, but not enough to be observing all night. There'll be some points where we'll see stars, some points where we won't, and the transparency is supposed to be uniformly poor. So tomorrow I'll probably send out an email to that effect. As far as going to Lake Hudson on Sunday, that's going to depend on how many people want to do it. I'll send out a message and then people can decide whether they want to go or not. And then it's the open houses in April. And I don't foresee a problem unless we've still got dangerous trees hanging over the road that we shouldn't be able to do that. The grounds are in pretty good shape. We certainly drive onto the turf and set up like we always have. And there is power to the observatory. The heat lamps were on when we checked it, and I think everything's in pretty good shape up there.
Did you have any more, Jack, or?
No,
Okay.
well, there's one thing
Okay.
about Lake Hudson too, is that
I would doubt very much if anything has been plowed down there, and we're supposed to get some more snow tomorrow. We don't even know if it's open. I mean, we know technically it's open, we don't know if it's passing down there.
Want to find out, that's something I can. That's only an hour trip and I have a pickup, so if I can't get through there.
So Adrian, are you saying you're going to drive to Lake Hudson tomorrow and see what the road conditions are in the park?
Yes. Yeah.
Okay, well, I'll wait for your report.
Yeah, tomorrow, I guess, because we want to see what happens after the snow hits the ground.
Where there's a lowbrow, there's a way.
Yeah, I didn't see a lot of snow in the forecast. I don't know that whatever happens tomorrow is gonna have much of an effect. I've gone down to Lake Hudson in the past in the winter, and you've been able to, everything was cleaned out and maintained. So I don't know why they wouldn't do it again this winter, but I guess if we're gonna invite people down there, we ought to be sure.
I seem to remember it not being bad, but I remember one trip I took, there was some accumulation on the ground. And I seem to recall being glad I had to pick up. So it could get bad, and it's worth checking out. We've had some melting.
Yeah.
So we just have to see where, if any kind of caretaking has been done, or if it's just been left alone.
Yeah. One thing I want to mention is that if it weren't for that one tree that had come down, that the road up from North Territorial would have been plowed out. The university had been up there and plowed out the road from the top, basically from the Stinchfield Road end of things. And they got to that one tree and they piled up a bunch of snow and backed out and went away and never came back. So Dimitri said he'd go up there and shovel it out, but.
Yeah, I made an offer, sorry, Jim, if like you guys say there's like a good possibility of us observing like someday during the weekend, I'll go out there tomorrow with.
Yeah, well, what I'm saying is I don't believe it's safe to invite people up there, given that we saw at least 3 more trees that could come down on the road at any time.
Yeah, I wouldn't do it this weekend. We may have to consider, once the snow melts off at the beginning of April, it might be worth visiting. Because then, no.
If we could get a crew of lowbrows together to deal with some of these, I think there's one we absolutely wouldn't want to touch, but the rest of them we could clear out if we had some ropes and chainsaws. But there is one that's just, would need a professional crew.
It's sitting basically, it's still in the ground, but it kind of, okay, imagine if you can, smaller tree here that's on an angle, and then it kind of just like is leaning like that over the road, and it was like on top of the tree stable, I would, but the angle is down, so this is the trunk of the tree, it's like that.
So it's
just sitting like that.
So it's a matter of weight and physics for it.
I don't, it's not, I don't think it's structurally. How big is that one? Not yet big. It's a tree. Is that the one you said we might want? That's the one where I mentioned to you if we needed like, get some chainsaws and cut it down.
Yeah, it's not like this though.
No, it's not. I would say it's about, so it's a small. Jim, how large would you say it is? I'd say like 8 inches. We can drop it over the road and then cut it.
How big was the tree?
That's what they would do.
Well, the one I'm most concerned about is just very tall. And
I'd say.
probably, it's not extremely thick, it's 8 inches or less, but it's very tall, and if it came down, it would block the road for sure, and if it came down on somebody, it would make them very unhappy.
Now, the other question is anybody gonna get ticked at us if we go up there and have at it?
Because we got the ability to.
Do we have the politics to do it?
Well, we took what was,
Shula's been pretty good about that for the most part.
yeah,
It'd be good if we let her know in advance.
Yeah.
and we should, some things are obvious, something falls and blocks the road. It's obvious what you have to do, but when you see trees that have lost their mooring and have been snagged by other trees and are just waiting to come down, that's a lot less obvious. And that requires a discussion and maybe some convincing to get, get the crew on the hourly clock to go up there and take that stuff down. To do it safely, it would take a while.
So it sounds like it's better for us to make sure the College of Engineering knows about it and would be willing to do something about
It's on.
that. Michigan weather. And that's to everyone here and to you, Jim.
Yeah, I think our go-to for something like this is Susula, isn't that right, Jack?
Yes.
Why aren't we hearing it on the system?
Yeah, Susula.
Because we logged out of this one, he left.
Okay, because the other thing, Jim, is that this was probably before you were even in the club, is that there were times when we went up and did work and we were told in no uncertain terms, we were stepping on somebody's feet. Yes.
Yeah, I think some of that is a little different. I think the main concern they'd have with what the problem we're facing now is that some of this is plain dangerous to do unless you have all the right equipment. Especially the one tree I saw, that does not look like something we should attempt with, at least not somebody who's in their 8th decade anyhow, should attempt to do without a lot of help.
I quickly input, my father, cut trees back in, overseas, worked in construction, had a business. I've helped him cut down many trees. A couple I remember worse than the one that's in. I remember, sorry to go off on a tangent, I remember one that was in a very bad shape that was like leaning over and a lot thicker. We have the equipment to do it. I think my family has the
But
equipment
I
to do it.
think we need the permission. I don't think we can go, this isn't quite our call. Let's do it. That's what I'm hearing. Yeah, if you go in and do it and you get a slap on the wrist, that's maybe. But I think to Darnell's point, and I think to some other points, I think if we have the opportunity to involve the College of Engineering, we should do that as opposed to, now, if the whole thing does fall, it's a different argument, but yeah, the fact that we could do it, if we got the permission from College of Engineering, yeah, go ahead and do it. We could then have a discussion and have your input on you and your father go up there, chop it up, and then we're good. But before enlisting you or your father's help, we need to clear that political hurdle.
Yeah, and then they complicate it.
Their number one issue is going to be liability.
Yeah.
Yeah.
Yes.
Yeah, if your father gets hurt doing it, and then.
But also, if they say we don't want to remove that, I can say that tree is a hazard. And I think Jim would agree, that's gonna fall.
Well, we could take this statement right now you just made, that tree is going to fall.
That's fair.
And we can take it, I know, Jack, you'd be able to say, we've got very good reason to believe that tree is going to fall, there's a danger.
Because we have the general coming up there for observing sessions.
Yeah, ideally, we could make an appointment with Susula and whoever she'd want to have along and just walk that road and say this, and this has to be dealt with.
Yeah, that's probably a good idea right there, Jim.
Yeah.
I like
Well,
that.
that's what I would propose for the situation. We're still a month out from open house season, finally having the public back, and they are going to want to show up. So,
Yeah,
if the meeting can be held, that would be a good idea.
yeah, I sent the blurb to the observers, so we're gonna have advertising out there for the April open houses, whether we're ready or not.
So that makes it even more, I guess, it's get a little urgent to say, hey, let's deal with this tree. Hopefully, it'll get a little bit warmer and we won't have a snow issue. And things will line up for the open house in April.
Okay, just to add something to that, like I said, on Tuesday, I did get an email from Cecila Fernandez. And she said because I sent her some pictures about the tree down there. Because when I was there, those trees are still down. The issue is, she had told me that their people were gonna go up and start removing those trees to get to clear the road. And the road's the one issue they have to keep clear.
Okay.
Now, I don't know when they're gonna do it because there's been some continued snow up there during the week. And tomorrow, according to the change in the forecast, you're gonna get snow for part of the day on Saturday till almost midnight, starting in the morning, off and on. So
It's gonna be that heavy snow. 'Cause we're-
I don't know if they're gonna have anybody out the weekend to do any work there, probably not. So, I know she sent them out there, but I don't know how many other areas they have to fix before they do that.
Well, I suspect any snowfall it's gonna be heavy enough to start making it.
I don't think we're supposed to get a lot of snow though.
And if U of M property is anything like my street, they
Really?
still have.
1 to 3?
stuff on my street from the ice.
Tomorrow.
When, I was driving down from my house to be found, I just saw power line down, like everyone's swimming there. By the time I drove back, it was gone, but it's like, there's still trees falling and.
Yeah, what I'm seeing on the NOAA weather for the area is less than an inch. I think it's more hazard if you're out driving around in it than anything else. I don't think we're gonna have accumulations that we have to worry about.
Right.
Yeah, this forecast, the Bureau Weather Channel says more wind, which could be another issue, but
Yeah,
it's not showing snow so much as it's showing gusts of wind.
yeah. We're not gonna be up there tomorrow anyway, so.
True.
Yeah. Yeah, and Sunday does look perfect from sundown to sun up.
Yeah, it's an ideal night for the marathon,
Yeah. Yes.
except,
Messing with plans to catch Milky Way rides, but you can still see Milky Way rides pretty well at Lake Hudson. But this was mine is meant to be over some deep water. So I still like it, but it sounds like a perfect night.
yeah, if I'm not the one that has to take the telescope back to the 17-inch back to the observatory, I'm certainly happy to pick it up and take it to Lake Hudson. But it would require someone else that I could give the telescope to who could get it up there.
My comment, Jim, is that you can enjoy the Messier Marathon with just your own telescope.
Well, yeah, that's not the question. We did all this work, and the idea was that we'd put it through the acid test for the Messier Marathon and then dump it back, return it to the observatory, and it would be ready for the open house.
Yeah, I don't know if we have any takers, and see my truck full right now, although I have taken a lot of things out of it. So unfortunately, I don't know that I could offer, my pickup and
spot to get it back.
Yeah. I didn't expect, volunteers to do this to be lining up, so I think we'll just have to leave the telescope in Dave Jorgensen's shop for the time being. He's been very generous and
There's gonna be plenty.
I think when the hill is ready for regular vehicles to go up and down it is when we'll move the telescope.
Yeah. One more for Dimitri, last one, I promise.
Oh, sure.
Would it, would it help at all if I was to get a photo of the tree in question, just to send the email so you guys know what you're dealing with? Because it's not dangerous for me to stand 20 feet away with a photo and snap it.
Yeah, I don't think it's dangerous for somebody to be up there during the day who knows that they have to be careful. I don't think that's a problem. Our real problem is having people up there from the general public or even the general membership and think something happening while they're there that most likely would, trap somebody up top.
Yeah, anything.
That's the most likely thing that would happen. That would be unfortunate.
Chop that tree out. I don't think will hurt anything, if you want to do that, but you could, it'd be stupid, but you could take a ladder and some, like, I'm really tired, I apologize. What is it you use like in the back of the pickup truck to secure the strap? It's a winch and, no. Yeah. You could nothing further than observation at this point. Yeah, there's no other way, you can't really secure a half fallen tree. So there's nothing we could. Yeah, solving for how to get rid of the tree.
Yeah, without a cherry picker, you'd have to secure the tree with ropes and then start hacking away at it from the bottom. And
Yeah, those are things to keep in mind if we get the go-ahead from the College of Engineering to do it, which it sounds like, Jack, they're already trying to hold themselves.
I know they are because you gotta realize guys like Professor Kupperman that work at the radio observatory, you have to be able to drive up there at least at times to do their maintenance.
Yeah, I think we can agree, the only thing we ought to do is make sure that we draw this dangerous situation to their attention, because if they only focus on a clear road, they may miss it. So I do.
Well,
I don't think it's missable. It's pretty easy. Yeah, they might be like, oh, it's not falling yet. You never know.
Anyway.
good
Okay.
windstorm,
Yeah.
All right. So moving on, Doug, do you have anything for us?
I thought this moment would never come.
Yeah.
So we still have 199 memberships and we have lots of money in the treasury despite spending about $540 on the 17.5-inch refurbishment. So that was with the new batteries for the mirror box, the new encoder, miscellaneous little other things, and then the Kendrick system for the Juminator for the do control stuff. So, and that's the money part. The best part was Jim, Jack, Doug, Dave Jorgensen, Don, everybody that was involved in doing that work. A lot of stuff was done for free, not to mention the labor. So congrats to all you guys. I hope it all works, and sounds like it should have a good scope again. But
Open house based on how we transport it.
I could not hear any of that, but
Have to wait till open house to transport it.
yeah. So anyway, that's the treasurer's report. I'll send the email to whoever's taking the minutes. Adrian, are you taking the minutes?
Davis.
Oh, Davis. Okay. I'll send it to Dave. And then the only other thing is I thought I caught our speaker needs a size large t-shirt.
Yes.
Yes.
Yes, I was gonna ask if you caught that. Thank you.
I did. Yeah, so
Cool.
I don't have any of them with me, and Charlie, apparently you don't have one.
Yeah, I don't think I've got, I'll double check, but I don't think I've got
Yeah,
any.
let me know if you do or not, but either way, I can send one if I need to when I get back in April, second half April.
Yeah, that's why I told him it might not be until May or something, so.
Yeah.
No, I don't know, so, okay, cool.
Okay, all right, that's my report.
Thank you, Jeff.
Last but not least, you guys are all familiar with this piece, and I'm gonna add $229 to the expenditures for this month because we got on to HostGator. We got ourselves a WordPress site. And next screen, with our communications committee, we'd come up with these little points for some menu items. And in kind of messing around with things, we now have an actual site, which is at lowbrows.club for the time being, because we're going to, fill it in from the old site as we see fit. We've got a number of the pages that I just kind of filled in, complete with maps to the new Detroit Observatory. Our past meetings are all the meeting schedules all here. And this is all easy enough to customize, where you can edit the page right away, go to a dashboard thing in WordPress, and take care of the entire site right from there. So that is where we're at. It's very preliminary. Obviously there's, we got blank pages for all kinds of stuff here. We did get some Peach Mountain things in here with maps. But as we fill it in, we get a structure that's kind of sound. Then I'll get with the rest of the communication committee and anybody else who wants to help out, and we'll start moving some material in once we kind of have that structure down. But we have a start.
Yeah, it's live. I just went to it.
Excellent.
Yeah.
And I would add, yeah, I did send you the money for that, so I assume you got it.
Received. I just got to put it in my bank account, so it's there. Thank you.
This is all because we're no longer able to be hosted by.
We are being able to, this is our current website with University of Michigan. It's frankly, it's tedious to edit because we have one person that can essentially do it because he's got the files. The university is being very wishy-washy about the service that they're offering, as they're talking 24, possibly 25 of just discontinuing the free service altogether. So that's why it's like, we were kind of thinking about modernizing this thing and getting it so we have more members to contribute. So like, the observatory issues, Jack can post something and it'll go on a news feed. I was going to say this section in here, there's this big blank screen on the right side that did have some widgets in there. And I'm thinking like our news, what's going on, like the next meeting or, the current speaker, or the open houses. Yeah, all those widgets are and all that available. Like I said, this is literally 2 evenings worth of playing around and getting everything working and figuring out what to do with WordPress. But it's a good jumping off point, and I wanted to take the meeting to announce that it's finally happening.
All right.
Before we get people asking if we're going to have meteor watches, are we gonna do content?
Right.
Are we gonna?
I get that stuff from the Facebook Messenger. I get it from Facebook itself. I've gotten the Ask Lowbrows emails. Like, I think there's ways to channel a lot of that stuff.
And on top of that, I occasionally get people just call my phone and
Yeah.
ask stuff like that too.
You keep giving out your phone number.
Yeah.
Now we're a page here for this.
The site that we have right now is essentially $6 a month for the first 3 years. So we got 3 years on this contract. The lowbrows.club is, that domain exists for 1 year. So we'll have to decide in probably next February whether we continue that domain or not. Personally, I kind of like the idea of .club.
Yeah.
But we do have the .org right now that points to the old site. So I figure at some point we can switch .org over to the new site. And if we want to keep .club, that's fine, but it will expire in a year. But for right now, we got the two so that you can move data easily. And this was just cut and paste for the most part. Dot what? I don't know if that's an internet thing.
Yeah. I don't think that one's available yet.
Certainly valid. Now, I do have a spot for young astronomers. Yeah, in the menu structure there, and the thought there, we can put up young astronomers as a complete new, WordPress site if we want. The monthly fee goes up to, I think, $9 a month. If we want to do 2 sites, if we want to stick with 1 site, we can do this. And then youngastronomers.org is already pointing to a subset of the current Lowbrow page. So it's like, I see no reason why we couldn't continue with that. And then that tree just expands outward from that point. So this menu item is probably enough to get us started in that. And then we can decide later what we want to do with it. But the nice thing about WordPress is that every single page that you go to is a single page, so that you can rearrange them in whatever menu items you want. They all go all over the place. So it's very, very flexible in that way. But that's where we're at. That's really all I have. I think we had 27.
I showed 16.
We had 17 here
and 13 Zoom. I think I saw that point.
Yeah, Zoom, you have to subtract 1 because I'm on there double. I'm in person and on Zoom, and then total of 29 at our meeting today.
So you got total 29,
Yeah.
12 Zoom then.
12 Zoom, 17 live.
Do we have any data of how much the program, how much of the meeting is watched? Not on
yeah.
Monday?
I'm
just because we got 30 people, 100 and.
most
right?
most of the time, we got like a 30-60 or 33-66 split, 33% being in person, 66 in Zoom. And those videos do get watched. I can probably pull up the hit counts real quick. I think they have the watch statistics there. Yeah, current subscribers, last 28 days, we had 89 views of last month's video. So we are getting some hits on the YouTube channel, and I hear from various members once in a while. It's like, hey, thank you for putting that up because I couldn't attend today. I mean, myself, I've been in Mississippi on meeting night, and I was able to view the meeting and put it online. And I mean, it was great. I didn't miss anything that way. So it's not much trouble. Like right now, Zoom, you basically say record, it puts it off in the cloud. After the meeting, I'll download the thing and then, trim it up so all the junk on either end isn't there. And then I upload it to YouTube, fill in a few fields and done.
Right now.
Exactly. No, this is part of the meeting. It's that stuff at, from 7 to 7:30 that we usually end up chopping out. But sometimes the meeting is a little late. And so I just find that place, chop it and, put it up. So it's really not too much trouble. But that's probably one of those things that goes under, online coordinators' duties. So, but if you got any questions on the thing, just email me. If you want to help, of course, raise your hand and we'll put you to work in a month or so. I just want to get the structure nailed down before we, start filling in all kinds of crazy stuff. So
cool.
Anyway, that's what I got.
It's off to a start. Thank you, Jeff.
Yes.
So while we're on that subject, I'd like to talk about the existing website. So as at least the officers should know, we started phasing out the printed and mailed copy of the newsletter. So I've had a couple renewals where I say, well, unless you really, really, really need it, we're not going to print and mail it anymore. And so far, everyone has sort of cooperated and haven't caused any problems or objected. But one of the things I say is, well, you can go onto the website and look at the latest newsletters. Well, the last one that's on there right now is March of 2022.
Yep.
So we're a year behind on that. So is there a way we can get the latest year's worth of newsletters put up on the existing website?
Yes to both. And my thought is to go through for the new site and, get those things online there. For the old site, I think it's just a matter of editing that page and getting those files downloaded, because on the server itself, 2012, I think is the last one that I see. Or at least I'm the directory I was looking in anyway. But
Yeah.
we can get those things online if I know where the repository of PDFs are.
Because if I'm telling people, well, you're not going to get it in the mail, but you can go on the website and find it. Well, they can't. And that's sort of the point. So until we get switched over, unless you think it's going to happen within a month, or
Well,
do you think it's going to happen within a month?
No, I'm not insane.
Yeah.
I'll look at that. That was probably my next focus is, seeing what the newsletter situation is, but I will say, after going through things and kind of looking in detail where all these things are in the current website, there's a lot of material that's out of date.
Oh, gosh, yeah.
Or it points to nowhere. It does need kind of a clean out, and this is an opportunity to take what we need and not worry about the stuff that's old. I mean, there's
in fact, for an example, look at the photo album of pictures of members.
Yeah.
Half those people aren't members anymore, and the ones that are up there, they don't look like that anymore.
Yeah.
I know I don't.
Yeah, I saw some of those too. I didn't recognize.
It's kind of funny. It's kind of fun to watch.
I think they're valuable for, antique photos or, founding father photos or something.
Yeah, it's cool.
Yeah.
But yeah. I think it's all going to get looked at, but as far as the newsletters, that was kind of my next focus, just because that is one of those glaring things.
Okay.
And I gotta locate the collection wherever they are. I'm sure Amy or somebody.
You'll have to go to Amy to get them.
Okay.
Yeah.
But
even in particular, the latest ones, the last years at least, ought to go up there. Ones from 20 years ago, they should go up there eventually, but the most recent ones, the latest ones are more important, I think.
For the past meeting videos, this is what I started doing here was that, they basically go in reverse chronological order, and they've all got a YouTube link that you can click on, and it'll take you to that video. We can do something similar with the newsletters, have, years and then the various months. There's probably some standardized way to do it like that in WordPress, but there's duly noted, I think. And that's one of those sore areas that, if you want to look at the old newsletters, you just can't. They're hard to find. Anyway.
Fair enough.
I'd like to entertain a motion to adjourn.
Second.
All right.
Third.
No objections. Doug Nell's not here to object, so we are adjourned. Thank you very much.
So long.
Thank you for hanging in there, guys.
10 o'clock.